we're live. I always forget to do this. Let's see. What are we saying? The second, my second office hours for the module. Twitch.tv/pwn.college. Awesome. Tweet. Twitch. Okay. Let's see. We have people on Twitch, people on Zoom. I think we're basically good. All right. So, let's roll. What do we got? Okay. So, just to catch everyone up, we are currently on that's not my fascinating. Okay, that's the wrong browser. 1 second. How's this fucking possible? Every single fucking time. Okay. No, I see. Because this guy... Hold on. Have to change something. OBS just needs to be reconfigured every single time. Okay. That has changed. What the hell? How is this possible? Okay, thank you. Yeah, now it works. Okay. All right, so we are on still not working. Great. Okay. We're on week 8. We are currently on the tentative... What? No, this should work. Okay, good. Okay, whatever, I give up. If it works, it works. We're currently on the second week of the wildcard module. Excuse the communist meme there. That is a pretty good meme because we had to put some schoolwork on voting week, unfortunately, because we had to extend the combination module slot by an extra week. So, we're on the second week of the combination module. Let's check in real quick with how things are going there in general. We have 15 people solved the whole thing completely, which is awesome to see. We'll put some memes over there. That's pretty good. So this is solving through level 8. Level 8 is a JIT spray, and it is very realistic vulnerability, very awesome to see people actually tackling that. That's incredible. That being said, all of these levels are pretty tricky. We managed to up level 1 to 105 people that have solved it. Out of those, let me check exactly my notes. I tracked down how many were actually were ASU students. 89 of them are ASU students so far. That's also better than last time, but I would like to see it even higher. We walked through level 1 start to finish, 100% in between office hours, the first Q&A, everything. Like literally every single keystroke you have to write to solve level 1. There should be no excuse for not having level 1. Level 2, Connor solved in his office hours. Level 3, I solved in my previous office hours. And I think you solved it again last Q&A. Then I talked about level 4. But then I think we'll talk about level 4, 5, 6, 7, and 8 a little more today. So let's catch up on some questions. All right. First question. What should we do if even with the level 14 Jan guides, we're still having trouble with them? Odin, are you having trouble with level 14 with level 14 after the level 14 Jan guides, or with the testing, or with the toddler modules after seeing the level 14 Jan guides? My advice, if you watch the Jan guides and are still having trouble with the level 4, 5, 6, 7, and 8 challenges on toddler 1, go back and at least do level 16 on baby rev. So make sure, so level 14 video walkthrough, follow the video walkthrough, solve level 14 and 15 and 16, and then do the toddler challenges. All right, then we have if you're not given the level 7 teaching binary, how could we spot the vulnerability in level 7 testing? What's so important about the teaching binary in level 7? Let me take a look. First of all, what's the difference? All right, everyone that has solved teaching has solved testing. Boom. Okay. Right. Level 7. Zero, why do you think that you need the teaching binary to spot the vuln in level 7 testing? Unless there's an unintended vulnerability that I'm unaware of. All right, if you're thinking of the same vuln that I'm thinking of, yeah, I can see that the testing binary makes it easier. What I would say on a general note is this output that is produced by the teaching binary can be replicated 100% by using a GDB script, right? So let me show you real quick how to do that without writing a full solver. So let's just for this guy. All right. So we start a screen session here. All right. So we have a tracer for level 7 teaching 1, and let's just show briefly how this might work. If we disassemble instruction interpreter loop, yeah. So here's the function interpreter loop. As a reminder, I guess I jumped ahead a little bit. Let's open up one of these in Binary Ninja. And this goes for Yan 85 in general, not just for level 7. Yan 85 up until level 8. Level 8 is a JIT, but until then, we have a bunch of interpret functions. And what makes the teaching binaries unique is that they print out a lot of good stuff. So in the loop here, it would actually print out at every. Let's actually take a look at it. In the interpret loop, or in the interpret instruction, it prints out the values in all the registers and so on, right? So we can do the same thing here. If you disassemble interpret instruction, interpret underscore instruction, and we see. Is this teaching? This is teaching. I apologize. Let's log out and restart it in testing mode. Oh, can't see you can't see my screen. Okay. That is now started up. Oh, it's tracer, right? Didn't get saved. Okay. So if we disassemble interpret loop, interpret instruction. Interpret instruction has a bunch of handlers that it calls for different instructions, right? And in the Binary Ninja analysis, we can see that at the beginning of every handler in the teaching version, which is right here, if you go to interpret immediate, you see right away that it prints out a log, right? And says, okay, there's a immediate instruction, and then it has, this register equals this data. We can do something similar in GDB. I'll get the beginning of this, and then we'll move on. But basically what you can say is you break at interpret im. And you put the command as a command. You put puts, what's the format here? S im. Let's just start it out like puts. What am I doing? Printf, s im, new line, end. And we just go all the way. We have interpret im, interpret add, interpret stack interpret STM, and we've got continue here. So as it hits each of these handlers, it will print out a trace. Here are the syscall, or here are all the instructions. We update this. Okay. Now we load that script. Okay, it runs it hits the breakpoint. We run it. We input our code. And it did not trigger the breakpoint. Why not? Let's break and crash. Oops. Okay, that's 2 breakpoints to crash. Run it. Okay. That time it triggered the breakpoint. Did we miss? We must have missed a. We missed one. Comp. I must have triggered a comp. That's actually, let's put it in the same. Okay, so in my GDB script, I'm building out a tracing program that in the testing level reproduces what the teaching level would print to me. Let's restart this. I just run it, and I put in a bunch of A's, and we got into the comp, and then the machine crashed due to unknown register, right? And then I can build this out more and more. In fact, arbitrarily complex prints here. So for example, if we go to comp in Binary Ninja, and we say this is for, this is for teaching one. For testing one, if we go to comp, and we say, okay, let's see, we will call read register with, and as we know, read register takes the state as the first argument, and we know this from the Jan 85 walkthroughs and tons of previous office hours, and then the register as the second argument, right? And that comes from EDX, which comes from AL, which okay, and then EAX comes from the data stored at RBP minus OX1E. Okay, so let's get that in here as well. So here we will print 1 byte. That is the format string for 1 byte. The C format string, which is what GDB uses as well. This is half. So by default, X is 4 bytes that it'll print. LLX is 8 bytes. HX is 2 bytes. HHX is 1 byte. And then we will print RBP minus OX1E. Actually, it depends on where the breakpoint happens. The breakpoint happens at 1, 2, 3, 4, 5, 6. Breakpoint 6 happens at 666. Right at the beginning. So before it allocates the stack frame. So actually, before it allocates the stack frame. So this is where our breakpoint is. Of course, we can, have the breakpoint be after it allocates the stack frame, right here. But let's figure out. So it's at RDI is stored into here. No, sorry, RSI, the second argument stored in here. And then let's just print out the whole second argument for now, right? So we do LLX, RSI, right? So this is the beginnings of our tracer. Run, give it a, cool. So this is what it received. Comp, and then 4-1, 4-1, and 4-1. Okay, and now we can start messing with this tracer to, for example, extract the, we can shift this, we can say RSI and OXFF. This gives us the lowest byte of our instruction. Okay, or if I do that and then go ABC, so that is, I accidentally triggered an add instead, so obviously BAC, there we go, comp, and then a 42, so that's like the least significant byte because of little endian, and then we can do RSI 8, OXFF, and that's the second byte. Okay, something is not correct there. 42, 42. Oh, oops. I needed to restart my script so that it reread the GDB script. That 41, that's the second byte of the instruction and so forth. But basically, as I reverse engineer the code and figure out what is what, I tweak this to understand what the instruction decoding is, what is being compared. I can, of course, call other functions here. I can define a function to try to name a variable, or try to describe a register, and then call that in here. And basically, using GDB script, build out a tracer to replace what was lost when we went from teaching to testing, if I wanted to do that. And then using that, of course, discover the vulnerability. Hopefully that helps at least a little bit. I'd like you to consider that you will absolutely need to use GDB very heavily in this assignment. 99% of the questions we get can be answered by trace it in GDB and see what is happening exactly. Because that is just an inescapable necessary skill. Okay. Zero, you might have found an unintended vulnerability in level 7. That was not the vulnerability I was intending. Interesting. Interesting. Yeah, that's definitely an unintended vulnerability. And I think I know why it happened. I'm going to have to fix that for next year. Yeah, so Zero, actually, go back and try to solve it without that. It's a very fun challenge without it. All right. So, dang, a lot of people use die equals 0. That's unfortunate. Well, what can you do? Unintended vulnerabilities happen. Okay. I'll tell you what, because there's an unintended vulnerability, I will show off in level 7 where the intentional vulnerability is. And it's right here. Let's look at this in high level IL. Wow, that looks horrible. All right. You obviously can't do read code syscall, because then you could just read in extra code and be done with it, and bypass the single syscall filter. In level 7 and 6, if you look at main, there's an extra filter, and it does this, and this looks like insanity, but if you look at it in assembly, it's actually it's a single loop that goes through your shellcode and makes sure that you only have one single syscall instruction, and that's it. So you get a single syscall instruction in your entire shellcode, and then you have to get the flag that way. You can get the flag with a single syscall instruction. There's not intended to be any memory corruption vulnerabilities. I think I actually understand where I messed up that there is. But if you look at the way that interpret sys works, it says if the argument has some bit set, and of course this bit varies for every variant, then, okay, let's say if the second argument has, in my variant, the fourth least significant bit set, then we do an open syscall. If it has the second least significant bit set, then we do a read syscall. If it has the third least significant bit set, then we do a write syscall. If it has the fourth least significant bit set, or whatever, the fifth least significant bit set, then we do a sleep syscall, and so on, right? But what does it not do? None of these cases return. That's where the vulnerability is. Cool. Okay. So that's level 7, 6, or sorry, that is level 7. Level 6 has an intentional memory corruption vulnerability. Okay. So then, for level 6 and 7, let's launch a teaching level 6. It tells you very, very clearly. So this challenge allows you only one sys instruction. Sys instruction is a YAN85 instruction. It's not the x86 syscall or anything along those lines. And you can, again, just like with 7, if you open up level 6 in Binary Ninja, sorry, if you open it up here in main, we count from 0 to OXFE. This is where the vulnerability is. I guess the unintended, kind of. And we go through, and here we load here we go. We AND the instruction byte with hex 40. In my variant, hex 40 is the sys opcode. We test if that is 0. And if it is 0, if it is non-zero, we add a syscall, add 1 to a counter of syscalls, and then we check to make sure that that counter is less than or equal to 1. So you only get one syscall in the in your shellcode. So then there's some questions, right? Could the syscall instruction be disguised? So, can you override it? Similar to one of the shellcode baby shell challenges for x86-64. For level 6, there is a memory corruption vulnerability, as the level tells you, that should let you get extra syscalls. For level 7, there's no intended one. Apparently, there is an unintended one. All right. Let's see what else we got. All right, looking back in questions. Okay, yeah, I see someone had trouble with the baby rev level 14, 15, and 16, even after the level 14 walkthroughs. I'm not sure what to say in that sense. You should go back and follow those walkthroughs very carefully. Make sure, just directly. There's a 5.5 hour one. I guess if you have to do the full 5.5 hours, just follow along every click. Your variant will be slightly different, but and you'll have to adjust for it, but you'll have to follow that along. Otherwise, ask on the help channels if you have specific things that are unclear. That might work. But you definitely need to understand the emulator on a pretty deep level in terms of reversing it to understand levels 5 through 8. All right. So, Connor talked about a jump table in level 8. Okay, let's talk about level 8. Level 8 is a neat level. In fact, I think level 8 is probably the most real-world applicable thing that you will have done in the course up until now. It's JIT spraying is a very, very real technique. And the question specifically in level 8, Connor, in his office hours, talked about a jump table in level 8. How do you find where the jump table is on the stack? Like many, 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 many questions, the answer is either a lot of reverse engineering or GDB, runtime tracing. So in terms of finding the jump table, let's open up level 8. Level 8 is unique. If we grab level 8, let's do testing one. And you open it up in Binary Ninja. instead of interpret instruction, interpret add, interpret loop, or interpret im, interpret add, etc., you now have emit. What are these? These are just-in-time compilers that take Yarn code and produce it and turn it into x86 assembly, right? So what happens is, instead of interpret loop, you have emit program that that will basically loop through your shellcode, and this is right here, and call emit instruction for every instruction. It also emits a bunch of initializer code up here. Emit instruction will go through and looks like just like interpret instruction. We'll go through, and depending on your what's it called? Your program, what instructions you send it, what Yarn code instructions it receives, it will call emit whatever instruction, right? So let's take a look at emit im. Okay, what does emit im do? Emit im calls this helper move immediate, which, I mean, looking through this statically is insane, right? So this is something very similar to write register. If you reverse write register a ton, you'll see the similarities, and it's kind of something a little similar, right? So here it says, okay, is the argument 1, hex 40, hex 8, these are all different bits set in the mask of a variable, of an operand to your Yarn code instructions. And you can even see it right here, unknown register in emit immediate. It's exactly the same as in write register. And when it does emit, what it does is very interesting. It emits into RAX hex 49, then it adds, it writes to the pointer pointed to by RAX hex 49, then it writes, increments that pointer, it writes hex B9, increments that pointer, and then goes back to here where it'll write something else to that pointer, right? So, of course, what we're doing here is just-in-time compilation. If we go to main and we see where it calls emit program, right? It passes the one argument to emit program, which is the VM state, similar as for interpret program. But one extra thing it does here is memory map at OX1337000 executable code, or an executable page where to store the emitted code. So let's take a quick look. If we go, and then it will indirectly call that code. It'll call RDX, it gets RDX out of RAX, it gets RAX out of this var 818, and var 818 is where it stores the output of mmap, right? So this is our executable page. Boom. And and this executable page, I guess, also is actually, if you let me frame my thoughts. So it stores the executable page into RBP minus hex 810 over here. It loads another variable, the address of RBP minus hex 2810 into RAX, moves that into RDI, and then calls emit program, right? So RBP minus 2810 goes to emit program. That is hex 2000 away from where the executable page is stored. If you go here, you will see this hex 2000 right there. It indexes into it to pull that into RAX, store that into var10, and then read that into RSI and pass it as the second argument to help or move immediate. So the first argument to help or move immediate is the VM state. The second argument is where the mapped page should go. Okay, cool. So this help or move immediate is actually interesting because we have which case were we? Yeah, this case hex 40. No, whatever, either one. So let's look at hex 20. If the register is hex 20, this emits into the writable page, into the executable page, 49 BF, and then a keyword, 8 bytes. Let's take a look at what this might be. I just have my disassemble shorthand, and here it was 49 BF, and then 8 bytes. Sorry. Let's write this to a file. That's our mystery file. There it is. 49 BF and 8 bytes. And if you disassemble my mystery file, move absolute, basically move R15 into R15 of this variable, right? That's pretty cool. So that's if we, that's what is emitted by help or move immediate, right? So this makes sense. Moves an immediate value into R15 if var20, evidently the operand is hex 2. Let's see if it's hex 8 instead of, it's 49BD instead of 49BF. Let's take a look at what that does. 49BD moves it into R13, but this variable, this value, that presumably is an argument to our im instruction. Let's take a look what else. If we go hex 40, then instead of, it's 49BC. R12. So what we have is a just-in-time compiler that is generating byte by byte x86 code from your Yarn code, right? And when you give it an immediate value, it will actually take the value you, when you give it an im instruction, it'll take the value you provide, and it'll emit that value into the, sorry, my mind just went blank. It'll emit a move instruction with that value into your executable shellcode. Someone's asking, is disassemble an alias for another program? Yes. I have a, it's a homespun one. I shouldn't be using homespun things on stream. Let me show you where it lives. Here. On my GitHub, under shell tools, I have a little shellcode helper that has assemble, disassemble. Yeah, you can look up a syscall if you're tired of going to Ryan A. Chapman's site. So I can look up syscall. What is open? That's syscall 2. What is syscall 2? It's open. What is open on ARM? It's 5, not 2. So yeah. Okay. Anyways, back to. Okay, so now we've kind of reversed this emit. What emit does, right? So abstracting, generalizing from what we saw. Of course, we can also look at interpret add. No, sorry, not interpret. Where am I right now? That's the wrong thing. What's going on? Okay, level 8, emit add. Similar things here. There's basically something that it emits. It calls another helper. This helper is gigantic and basically a monstrosity. The nice thing is that we don't need to reverse all of this. We can use GDB to understand what is being written to memory as our code is being just-in-time compiled. You have to use GDB in this challenge. There's no way around it. You can, with the, of course, with the teaching module, the teaching level, the teaching level is very nice. If we launch it up and go back to let's put in some code. The teaching level is very, very nice in that it will disassemble the result of the assembly, right? But it's a crutch. You should understand what is going on. If you run into any problems, trace them through GDB, figure out what is produced by what instruction, and understand what is, going on. All right. So someone asked about a jump table in level 8. There is a jump table, right? So you have these debug statements that are printed when code is being emitted, right? So instruction 1 is being emitted to 1237046, 2 to 04D, and so on. And this is because here's instruction 1 to 046, 2 to 04D, 054, etc. If you look at these locations, there's a counter that's constantly going up, right? And I didn't put in enough code to actually fill all of this stuff. In fact, I didn't put any valid code at all. I just put like AAA, right? The likely guess that you can make, and you would be correct, is that this is the instruction pointer being incremented. The Yan 85 instruction pointer that is being incremented, right? Let's take a look. Let's take a look to verify that hypothesis on how jump is emitted. So we can actually, first of all, under emit instruction or under emit program, every time we is it under emit program? Okay, yes. So in this loop, every time we emit an instruction, right? Every instruction that we compile, we first run through and do all of this weird stuff. And here you can see right away, there's a memory write of 49, memory write of C7, a memory write of C1, and a memory write of 4 bytes copy pointed to by EDX, right? And these are all going to RAX, and RAX always comes from RBP -8, right? So RAX is read from RBP -8, written to 49, then incremented by 1, etc. So let's disassemble this. 49, C7, C1, and then 4 bytes. C7, C1, and then 4 bytes. Okay, that looks like shit. What's going on? 49, C7, C1, oops, that's only one. 4 bytes. Okay. It's move R9 4 bytes. Okay. So at the beginning of every instruction, as we can also see from the teaching output that disassembles the just-in-time compiled code, we emit something that updates R9 with what we now strongly suspect is the instruction index. So let's take one more look. If we go to the jump instruction, we can see that there's this helper jump I that is called from the jump instruction. Let's actually see where else it's called from. Over here, if we are hovering over helper jump I, you can see on this bottom right here, bottom left here, that it's called from several places. From edit LDM, or emit LDM, from emit STK, so emit load memory, emit stack, emit immediate, emit add, and emit jump. These are all instructions that can write to the I register. We go to immediate to see how it's done. It actually checks RAX is hex 10 after it calls move immediate. RAX is, let's see what RAX is. RAX is this arg3. Arg3 is RDX in helper immediate. In helper immediate, RDX, if you're going to postulate, is the, actually we can, in helper move immediate, we can see that RDX is used as the index, as the variable specifier, right? So the variable specifier here, just not the variable, sorry, the register specifier. All right, this register specifier here will tell us if it's 1, and these are all different masks, different bits set in a byte, which register to emit. And again, this is BF, which emits move R15, 49. BF is move R15 some immediate, 49 BE, move R14, 49 BD, move R13, and so on. Okay. Cool. So then in jump I, you say, okay. No, sorry. In immediate, it's easier to see that at some point there's a check against hex 10. And if RAX, which again, RAX is my, this arc3 is the register specifier. The register specifier is hex 10. Then we will not jump away from this block. We'll execute this block that calls helper jump I. Let's move in, dig into helper move immediate and see what happens to hex 10. Hex 10, hex 10 is right here. Hex 10 is 49, B9, and then whatever at 8 bytes. Let's take a look at what that disassembles to. B9. Move R9. So if the register specifier, and that register specifier, of course, varies per variant of the VM for your level. If the register specifier is a specifier that causes R9 to be emitted in the just-in-time compiled code, then helper move or helper jump I is called, and you can see that here, right? So if it's hex 10, which is what causes move immediate to be emitted, R9 to be emitted in the move, then we go into helper jump I, and helper jump I is a monstrosity. My advice is to break here in GDB and see what happens before and after. But let's take a look. Okay, so helper jump I takes 2 arguments, right? arg1 and arg2. All right, arg2 is stored in this RBP minus hex 10, and Binary Ninja tries to be very nice to us and actually tortures us a little bit here. By trying to track every different variable differently. This is let's see what happens when we decompile this. Okay, that's much better. So we write in what looks like quite a lot of code into presumably our the buffer. So we write in hex 27 bytes to our buffer. Let's disassemble this thing manually and see what it might do. This is going to be quite an undertaking. So first hex 4D, hex 89, hex C8, hex 49, hex C1, hex E0, then hex 30, no, sorry, just hex 03, hex 48, hex B8, then we have 2 bytes. So let's say AA and BB. Then we have 49, 01, C0, 4D, 8B, 00, 48, B8, Then we have 2 more bytes. Put C and D here. 49, 01, C0, 41, FF, E0, and that's it. So what just happened? I just went through all of this and typed this out into my shell. And over here, where it actually depends on my input, it looks like RDI is most likely. So this RSI is, or what is called RSI here is the compiled or the JIT location. It's my executable page. And then here, RDI is probably my VM state. Okay, so then I have my VM state here. And then I take 2 bytes from here, +9 and +10, and then we skip to +11, right? 2 bytes here, +19 and +20, and we skip to 21. I'm pretty happy that it didn't put a bunch of casts everywhere. Okay, let's disassemble this and see how many typos I made. I made typos. So it moves R9 into R8. It shifts R8 to the left by 8. So it multiplies to the left by 3. It multiplies it by 8. This is a common pattern that you see when you reference into an 8-byte, an array with 8-byte elements, right? And then everything goes bad. So then I put this 4-8, and then I have a B8. Oh, I messed up. I went from hex 9 to hex 11. That is not 2 bytes. That is 8 bytes. Let's put A1, A2, A3, A4, A5, A6, A7, A8. And then here is the same thing. Went from 19 to 21. That is not 2 bytes. That is 6 bytes. So we'll go B1, sorry, 8 bytes, B2, B3, B4, B5, B6, B7, B8. Let's disassemble that. This looks more reasonable. So then we move R9, which we now know is where our instruction pointer, our Yan instruction pointer lives, into R8. We shift R8 by 3. We move some large number into RAX. We add R8 to RAX, and then I screwed it up again after the 4D. 4D 8B. It's B8, not 8B. Okay. Nope. 4D. 4. No, it is 4. D 8B. This is 8B. And then if we disassemble it, let's here 4D 8B0048 8B00. Oh, I know what's going on. We cut off at the null byte for echo, of course. Okay, that is the limit of our that's the limit of echo. Let's just put in this guy here. Invalid X escape at position 0. Really? How's this an invalid X escape? No, that's valid. Oh, at position 88. Oh, how did I misread? 0 is 88. Okay. Sorry about this. My Control C. I thought I turned this off. 4B. This is 0, 1, right? Okay. No, that was not 0, 1. That was something important. 4D, 8B, 0, 0. That was where the null byte was. Okay, now we disassemble. All right, this looks more reasonable. We move some pointer into RAX. We add R8 to that pointer. Like I said, if we consider R9, we take the instruction pointer, we multiply it by 8, and we add it to a constant. And then we, and that constant, or not a constant, we add it, that's right. We add it to a constant that is determined at runtime, that is stored inside the VM state that's passed in. Then we dereference it. We load that into R8. We load another constant from another place of the VM state into RAX. We add R8 to that, and then we jump there. This is the code handling your jump table. This is where you should break and look. In GDB, as you emit any instruction that changes the jump, the instruction pointer, how it is emitting the instructions. Cool. All right. So then, this jump table is an important thing for hijacking the control flow, right? Because what happens is, you can see the code that's emitted for a jump instruction just reads something out of memory, adds something to it, and jumps there. That's pretty interesting. If you can overwrite whatever it's reading from here, then you can control exactly where it jumps. Okay? And maybe you can overwrite that. Okay, that's one thing. So now, let's say you use that to control where to jump. Now, where do you jump, right? How do you get code in there? Well, that part is very subtle, but actually extremely effective. If you remember, when we did the immediate here, this was what our move immediate disassembled to, right? And this would get placed somewhere in the memory math page, but this is also there. And this is the value data you control directly, right? So what if you jumped to that +2 right into the memory data you control? Disassemble that. That's some other stuff. You could make an immediate that is whatever you want. That is, I'm just going to start writing, for example, oh, my mind just went blank. You could make this. 4831 C0 0F 05. You could easily make an immediate im something, comma, 48, oops, 31 C0 0F 05. Okay, we disassemble that. Makes sense. Doesn't look very weird, right? This is easily a immediate instruction. You can create a Yarn code that will then be emitted to the page. And then if you jump 2 bytes in, boom. Code in executable locations that you control directly. One other caveat in level 8, as level 8 says, if you run it, this is a new version of Yarn 85. It's Yarn 85 64. Right? It is 64-bit Yarn 85. Otherwise, you'd only get 1 byte for your move instruction. But you can use 8-byte immediates. You can see that from the code as it reads it in. Cool. That is all the time we have. If you have more questions, ask on the help channel. Hopefully this wasn't just intensely confusing. I cannot stress enough that a lot of this stuff is much easier to understand in GDB than it is staring at disassembly. We got fairly far staring at disassembly here. But in GDB is where you would need to understand where on the stack or what offsets on the stack or what distances on the stack certain things are. Don't be afraid of GDB. You will need to embrace it more and more as the course goes on. All right. Quick look at 7 again. Is this 7? No. All right. Take a look at how sys is implemented in Yarn 85. Take a very, very close look. What are the possible valid arguments to its first operand? Right? Check how this is done. If you look at the decompiled code, there are values that will act differently here than you might expect, right? There's actually a common source of vulnerabilities, but you'll notice that none of these return after doing their thing. So execution will continue. So you can run the open syscall, and then this will keep running. Yeah, it'll return at the bottom, but it'll just keep running up until the bottom. Cool. So the question is, would I recommend looking at this in GDB or looking at assembly? Step through this function in GDB. Step through interpret sys and see what is going on at every single instruction in this function. All right. Question, what about level 4? Connor, did you cover level 4 in your office hours? Let's see, while we're waiting for Connor, is he on the... No, just 2 people in here. Maybe Connor's gone. Damn. For level 4, My advice is this. Take a look. Solve level 16 in Baby Rev. Because level 4 is just a purely more complicated level. It's level 16, but with a memory corruption. And then in level 4, take a look at how the read and write syscalls are handled compared to level 16. In level toddler 1 level 4 versus Baby Rev level 16. So go solve Baby Rev level 16. You will absolutely need that solution to solve toddler 1 level 4. All right. If there are no more questions, I will have to run. Remember, collaboration is open. Ask on the channels. If you have kind of specific questions, then we will do our best to answer. Good luck. All right, one more question. What's up? Go ahead and send it to me on email. I gotta bail. I have 2 meetings in the next 15 minutes I have to get through. What format? Yeah, Discord's fine too. Yep. All right, have a good one, everybody. Good luck. All right, let's see. How do we raid? If Connor's here, he can raid. Oh, lol. I see. We had an incoming raid. All right, well, we're done. So that'll be a cut. And, of course, you can go enjoy. Ciao. Good luck.